Welcome back. So in the earlier lecture, we have discussed about the introduction of this quantum error correction. Now let us discuss how to detect this bit flip error and how to correct it. Okay. So basically, what is this bit flip error? If you have qubit 0, so this flip to 1 as well as a 1 will be flipped to 0, something like that. Then first question is how to detect it. Okay, let us start. Now here, first I am taking the encoded circuit. Let us say this is a psi, which is alpha 0 plus beta 1, and here we have 0, this is 0. So we are taking this repetition of the qubits by using entanglement technique. So here C naught gate and here also C naught gate. So this will become alpha 000 plus a beta 111. Okay. Now let us suppose here we got some noise. That means whenever the qubit interact with the environment, so let us say there exists some noise. So how many types may exist? So here we can classify into 4 types. That is I. So that means there is no error in this first case. And the next one X tensor X are I tensor X, I, and this is I tensor I, and the third one is X. So here by seeing this, here there is a no flip, that means no error, no bit flip error. Okay, and here we have first qubit flip, and in this case here we have X, so second qubit flip, and this one we have third qubit flip. Now the question is how to detect it and how to correct. So first let us talk about the detection, that is syndrome detection. So in this syndrome detection, first let us take the circuit. Okay, so here we have 3 qubits because after getting some noise, so maybe first bit or second or third one may be flipped. Okay, so let us take 3 qubits. This is x1, x2 and x3. Okay, so earlier I have already discussed, that is uh, we are mapping from lower dimension Hilbert space to higher dimension Hilbert space by using some more number of qubits. Okay, so those qubits here we are taking as ancilla bits. So here we are having some extra qubits 0 0, and these are called ancilla bits. Sorry. Right. Okay, so let us consider this syndrome detection circuit. So here we have a C naught gate. Okay, and here the next one from the third one, right? So then we can take this is equal to, I mean this is S1, let us suppose, and S2. If you observe carefully, S1 is nothing but X1, because here, so observe carefully, this is X1 XR X2, and this S2, please observe here, C naught gates, and this is X2 XR X3. Then once you make the measurement, so once you make this measurement, okay, so you may get these values, that is either 0 0 or 0 1 1 0 1 1. Okay, now let us see how we will get this S1 S2 values. So if you want to get this S1, S2 values, now first, okay. So once again, let me copy that circuit here. Right. So let us see here. S1 is nothing but X1 XR X2, and S2 is X2 XR X3. So how to get this S1 S2? Okay, let me take just like a truth table. So I will consider like this. That means let us take X1, X2, X3 here, and here, wait a minute, X1, X2, X3, and S1, S2. So we know this S1 is nothing but X1 XR X2, and this S2 is X2 XR X3. Okay, so how to get this? Now if you take these values, 3 and 4 and 5, oh sorry, so let us consider here like this. Okay, so one thing is very clear, S1 is nothing but X1 XR X2. So you know, I think XR operation is nothing but inequality finder. So wherever inequality is there, we can take 1. So for example, if you see S1 is nothing but X1 XR X2, so that's why you have to observe X1 X2, and S2 you have to see X2 and X3. So here X1 X2 same, that's why 0 0 here, see this one. Okay, so that's why here it is 1, here also, sorry, here 1, here also 1, here also 1 1, but here same same, and here also same. And if you come to this S2, S2, that means you have to see X2 and X3 as these two. Okay, right? So here also same, but here different. See this one. Okay, right. So here also different, and the next same, same, X2, X3. Please observe X2, X3. And different, different, and again same. So if you observe carefully, we can form a truth table like this. So now we are talking about S1, S2. That means a syndrome detection. So S1, S2, we got like this, right? So let us take a 0 0 1 0, sorry, 0 1 and 1 1. So here what about the error? For example, if you see carefully, observe here S1 S2 0, this one 0 0, and here also 0 0. So there is no change in the bits, that means qubits. That means here we have a 0 0 and here 1 1. So that's why we can say here there is a no change. So no change. That means no change here, or no error, something, whatever it is. I'm writing it as no error. And the next one, observe this 0 1 here and 0 1 here. Then here we have 0 0 1, that means a third bit flip, and here we have 1 1 0, so here also third bit flip. So I can take this one as a third bit flip. So 0 1, third bit flip. And the next one, if you see 1 0, here 1 0, these two. Carefully observe 0 1 1 and 1 0 0. That means what? That the first bit flip. Okay, so this is the first bit. And the last one, next 1 1. Okay, so this 1 1 here. Here we have this 1 1. Okay, so if you observe carefully, here we have 0 1 0 and 1 0 1. That means there exists a flip in the second bit. So this is the second one. So once you make a measurement of this S1 and S2, for example, if you make a measurement here, then you may get S1, S2 either 0, 0, 0, 1 like this. These are the four possibilities. If you get 0, 0, there is no error. If you get 0, 1, there is a third bit flip error, and 1, 0 will give you the first bit flip error, and 1, 1 value gives you, and means it indicates that there exists a second bit flip error. Okay, right? So now here by using this syndrome detection circuit, we can detect which bit is having a flip. Okay, so let us represent this in a different way. So here let us take S1 and here S2. So this is 0, 1 and here also 0, 1. So the first box represent S1, S2 value 0, 0, and the second one 0, 1, and third one 1, 0, and fourth one 1, 1. So here this is we have 0, 0, 0, 1, 1, 1. That means there is no error here. Okay, so because of this 0, 1, we have third bit flip error. So that's why we can write it as 0, 0, 1, and here it is 1, 1, 0. So that means this is the third bit, and here 1, 0. So 1, 0 means the first qubit flip. That is 1, 0, 0, and here 0, 1, 1. Okay, and here this 1, 1, this 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 represent the second bit flip. Okay, second, and here it is the first. So that's why here the state is a 0, 1, 0 or 1, 0, 1 like this. Okay, in this way also we can represent. The next most important thing we have to discuss about stabilizers. Okay, so what are these stabilizers and what are these stabilizers? Let us discuss. Right. So what are stabilizers? Okay, so stabilizers. Stabilizers are nothing but Hermitian operators. So these are Hermitian operators whose square. So that means whose square is square equal to I. For example, if you take this x, y, z, something like this. Okay, so the Pauli matrix is whose square equal to I. And the most important thing, the eigenvalues. Eigenvalues lambda equal to plus or minus 1. That means if you have a stabilizer operator, it operates on a syndrome state psi, so you will get either plus or minus 1 psi. That means syndrome states that states are eigenstates of this stabilizers. So here this is a eigenvalue equation. Right. Okay. So now let us see some other properties. And the second point, first one is eigenvalues are equal to plus or minus 1. And the next one, most important thing. So there will be 3 stabilizers. Okay. So for example, in this case, I will discuss why it is like this. This is Z1, Z2, and this is Z2, Z3 stabilizer. So if you have these more than one stabilizer, these stabilizers are mutually commute. This is the most important. These mutually commutes. So what is the consequence of this mutually commutes? Whenever two operators mutually commutes, they have common set of eigenstates. Okay, they have common set of eigenstates. Okay, fine. So that means if Z1, Z2 is having a one state eigenstate psi, so that psi is the eigenstate of Z2, Z3 also, like that. Okay, nice. Now let us discuss about this stabilizers more clearly. Now again I am taking this circuit, that means a syndrome circuit. So here we have x1, x2, x3, and ancilla bits are there, that is 0 0 like this. And what we have taken is a C naught gate, and here also, and the next one, let me take another color, sorry, like this. We can represent the same circuit in another way, another different way. For example, if you see a C naught gate, so this is the C naught gate, okay, so this is X. X can be written as H Z H. H Z H is H Z H is nothing but X. So that's why I'm going to represent this as control Z gate. But here we have two head mod operations like this, head mod gates, and a control Z gate. So what is the specialty of this control Z gate? If control Z gate is invariant under interchange of control and target bit. That means here it is a control bit and here is the target. So we can interchange both. That means here it's like this. So this head mod gates are as it is. Sorry, represent with another color. So these head mod gates are as it is, but that control Z gate, control and target bits are interchanged. So that's why here it is like this. So if you take this one and how to modify this circuit. So here as usual, we have this 3 qubits, x1, x2, x3. One of that qubit is having error, right? And here as usual we have this ancilla bits 0 0. Now I'm taking this head mod gate here and here head mod gate, okay. So observe carefully. Earlier this is the target bit and this is the control bit, and here this is the control and this is the target. So now we are interchanging it. So that's why this is the target and here also target, okay. And similarly, if you take here, this is the target now and here is the target bit. So earlier control bits become now target bits and earlier control bits, I mean vice versa. Okay, fine. So of course one more head mod gate, we have two more head mod gates here like this. So both are equivalent. So here we can say this is nothing but like this, Z1 Z2 and this one, let us take Z2 Z3. Okay, so here Z1 Z2 and Z3 Z1 Z2 and Z2 Z3 are called stabilizers. So here the stabilizers Z1 Z2 operator and Z2 Z3 operator. So if you take this stabilizer operator and operate on that syndrome state, you will get either +1 or -1. So by using that parity check, we can say which qubit is having a bit flip error. And we can say like this also, that is Z1 Z2 operates on psi, this is -1 whole power S1. If S1 is a 0, you will get a plus parity. If S1 is a 1, you will get a negative parity. And Z2 Z3 operates on syndrome state, that is -1 whole power S2 psi, the same. So finally S1 and S2, if S1 equal to 1, so here we will be having a parity change. If S2 is having a 1, then Z2 Z3 operator is having a parity -1, that means eigenvalue -1. If both are having I mean S1 equal to S2 equal to 1, then both are having the negative parity. Okay, so this is the way of I mean this is the nothing but the stabilizers, and the stabilizers are the eigenstates. I'm sorry, stabilizers are having a eigenvalue equation with eigenvalues plus or minus 1. Okay, right. So let us continue. Now here we can represent this parity check like this. So here it is S1, S2. Just now I told you this S2 is nothing but minus 1, sorry. Here this is corresponds to Z2, Z3, and here it is Z1, Z2. Stabilizers. So here 0 and 1, S1 can take 0 and 1. So we have already represented earlier like this. So here it is 0, 0, 0, 1, 1, 0, 1, 1. Now here we have 0, 0, 1, 1, 1. So a 0, 1 will give you third bit flip, that is 0, 0, 1, 1, 1, 0, and this one first bit 1, 0, 0, 0, 1, 1, and here it's a second one 0, 1, 0, 1, 0, 1. So now by using this discussion about this stabilizers, already we have discussed like this: Z1, Z2 and Z2, Z3. That means if it operates on psi, we will get minus 1 whole power S1 minus 1 whole power S1 psi. And similarly Z2, Z3 operates on psi syndrome state minus 1 whole power S2 psi. Now let us discuss. So here we have S2 0, 0, 1, and here we have S1 0, 1. S2 0, that means definitely plus, okay, and S2 1, so minus. So here minus 1 whole power S1 plus, and here it is minus. So now if you observe carefully, these are syndrome states here, these states. Okay, so there is no change in the first one, and if you take these two states, for Z1, Z2 we have plus parity, for Z2, Z3 we have this minus parity. We can check how it is. Let us see one more time. So I'm taking this, okay, so Z1, Z2. So third one, actually here we have 0, 0, 1, okay, so third one we can take it as I3, okay. So here Z1, Z2, first two qubits are 0, 0. That's why there is no issue, there is no parity change, so that's why plus 0, 0, 1. But if you take Z2, Z3 and sorry, Z2, Z3, and what about the first one? First one is nothing but I, okay, I1 we can stay, yeah, 0, 0, 1. But in this case, if you observe carefully, so Z3 operates on this 1, you will get minus parity 0, 0, 1. Now if you carefully check this, Z1, Z2, okay, operates on 0, 0, 1, you got plus parity. Z1, Z2 operates on 1, 1, 0, sorry, 0, 0, 1, you got negative parity. Like that we can check. Let us try one more. So here I am talking about this this one, because both are having a negative signs. Let us discuss. So if you take one more example, so Z1, Z2, and I3 operates on 0, 1, 0. So here Z2 operates on 1, so you will get minus parity 0, 1, 0. And similarly Z2, Z3, the first one is I, so 0, 1, 0, here it is again, this Z2 operates on this, we get minus. Similarly you can check the other one also, this one also you can check. Fine. So now we understood what are these stabilizers and how we are checking the parity by using these stabilizers. Okay, stabilizer operators. Stabilizers are nothing but the Hermitian operators basically. Okay, right. Now let us come to the final stage. If you observe carefully, first what we have done is first we encoded, that is the first step whatever we have discussed here, the transformation. So that one we have done, and the next one syndrome detection we have done, and the last step the correction. Okay, let us start that. So the finally we came to this correction, how to correct it. Okay, and we have to use only those gates which do not disturb the original information. Okay, right. So let me take again the total circuit. Right. So this is our earlier syndrome detection circuit. Now once you make the measurement of S1 and S2, we got these values, so 0, 0, 0, 1, 1, 0, 1, 1, like this, 0, 0. There is a no error, so that's why here 0, 0, no need to do anything, just leave it. This one, leave it. Next one, 0, 1. If you have 0, 1, the third bit is flipped. So that's why, so what I am taking is, so carefully observe. So here it is, this one 0. So that's why I'm taking here like this. This is anti-control. Okay. So I mean, if anti-control means if it is a 0, then only it will be changed. Okay. So here it is a control because it is a 1. And which bit is flipped? Third bit. So that's why I'm going to take this third bit like this. That is a 0, 1. And the next one is a 1, 0. If it is a 1, 0, first bit flip. So that's why we have to correct this first bit and observe carefully. Wherever 1 is there, take control. Wherever 0 is there, take anti-control. Sorry. Like this. Okay. And the next one, the last one, 1, 1, that is a second bit flip. So we have to use a NOT gate on this second qubit, and both are 1, so that's why just take like this. So if both are 1, 1, then it will flip the second bit, and S1 is 1, S2 is a 0, it will flip the first qubit, and S1 is 0 and S2 is 1, it will flip the third one. So like this we can correct the error, right? And once if you see the output here, it will be alpha 0, 0, 0 plus a beta 1, 1, 1. Okay, so that's it. So this is here we have a syndrome detection. This is the detection. Okay, by using the by measuring the S1 S2 value, we are detecting what error exists. I mean which bit flip error exists, first or second or third. And after that, this is the correction. So by using this, we are correcting again that bit flip error by using this control gates. Okay, right. So I hope you understand what is the quantum error correction and how to detect this bit flip error and how to correct it. Okay, so now let us take the circuit in the simulator. Just wait, please wait. Now let us uh, use this simulator and let us take the circuit, quantum circuit here. So this one here, control. Okay, next one. Yes, here like this, and now remove this one. Right, fine. Okay, so here we have to measure this S1, S2. Okay, right. Now this is the syndrome detection. Now there is no flip error. If you see that first one, I request you please see that 0, 0, 0. So that's why here no error, nothing. Okay, and we have S1, S2, 0, 0. Okay, right. Now, for example, let us suppose take the there exists a bit flip in the second one. That means 1. So here the second bit got the flip error. So if you observe carefully, S1, S2 become 1, 1. So we have already discussed it earlier. Okay, right. Now how to correct this? So earlier we have seen that if it is a 1 1, you have to take the control, means okay, like this. I mean, control is not great. So we know that if it is S1 S2 equal to 1, then there exists a flip in the second one. Now if you check carefully, so again we got here 0 0 0. So although here we have 1, I mean second qubit, observe second qubit, okay, so then again we got it corrected to 0 0 0. And let us take the error in the first qubit. If you have first qubit error, that means it is a 1 0. S1 is 1, and here anti control and the first one. Again we got, please observe here, this one, please observe. Again we got 0 0 0. And for example, if you have error in the third one, let us take 1 flip, that's why it is 1. So this third bit flip error will give you S1 S2 0 1. So that's why anti control for S1 and control for this S2, and the flip will be here, the third one. Okay, again we have 0 0 like this. Okay, so I hope you understand how to detect the error by using syndrome detection, and how to correct by using this control unitary, I mean control gates. Okay, so thank you so much, and next video we will explain about this phase flip error. Okay, so thank you. Right, so we'll meet again in the next video, and we'll discuss about the phase flip error.